All right, so as we move into chapter 9, we're actually going to talk a lot about radicals, okay? Um, and so if you look at the next couple of videos, some of them will talk about adding and subtracting radicals or multiplying and dividing radicals. But today, all we're going to talk about is how to simplify radicals, all right? And so we're going to simplify some radicals expressions. So the first thing to know is, hey, what the heck is a radical, okay? Um, and so let's just say, for example, we have the square root of 45, okay? This square root sign right here, square root sign, as what we call the radical. And the number under the radical, so this 45, is what we call the radicand, okay? Don't ask me why they call it that, but that's just what mathematicians decided to name it. Now, if there's no number up here on this little shelf, we're going to assume it's a 2, okay? Later, we'll get into what's called cube roots and things like that. This would be an example of a cube root. But for today, we're just going to stick with square roots, okay? Just kind of like we talked about quadratics being a number squared. Square roots is the inverse of that, okay? So a few conditions we need to know when we are taking radicals, okay? We want no radicals in the denominator, okay? We never want to see no radicals in our denominator, okay? So that's one thing we never want to see. Secondly, we don't want, no radicands as a fraction, and we're going to talk about how to simplify that a little bit. Okay, no radicands as a fraction. And finally, the third one, and this is going to lead us into our discussion today. Our third one is going to say no perfect nth powers, okay? Where n, if we're taking, put up here, we're going to take the nth root of some number a. Well, n is just our index, or that little number on the shelf here. So we want no perfect nth powers as fractions of your radicands. We want no perfect nth powers left over. Okay, let's say left. Okay, so like Mr. Jones, I don't quite understand what you mean by all this stuff. Well, let's take a look at our example that we had up here with our square root of 45. Okay, if we have the square root of 45, I could write this as the square root of 9 times 5, okay? 9 times 5 being 45. So I really didn't change anything underneath this radical here. But, all right, so this 9 times 5, nothing changed here. But one property of radicals is that you can split it up into the square root of 9 times the square root of 5. And so we can actually ask ourselves, hey, what number times itself equals 9? Well, on that, you'd tell me, oh, it's 3. And then we'd have to ask ourselves, is there any number times itself that equals 5? And the answer is no. So we're just going to leave that alone, okay? And so now we can go back to our 3 conditions. Well, there's no denominator, so this first one we checked off. There's no fractions. They're all whole numbers, so we're good. And if we look at this 5, there are no perfect squares. Think about your perfect squares. 1 squared is 1, 2 squared is 4. So there's no, and 3 squared is 9. There's no perfect squares that are factors of 5. So this would, 3 times the square root of 5, this would be our simplest form, okay? Let's try another example of that. So this time we're going to say, hey, all right, what is, I'll do it red this time. We want to know what the square root of 108 is, okay? And yes, I know you could put it in a calculator and you'd probably get, 10.3 something, yada, yada, yada. But we don't want the decimal. We want to get this radical in its simplest form, okay? So we're going to split this up just like before. We'll write a radical, and then we're going to write this as a multiplication statement, as a product of two numbers. Now, one of our numbers we want to be a perfect square. Again, our perfect square is 1, 4, 9, 16. 5 times 5 is 25. 6 times 6 is 36. Okay, we could keep going forever and ever. 64. Now, if I look at this, I know 64, and one trick, go ahead and pick the biggest square that is a factor. So we want to find the biggest square of 108. Well, 64 isn't a factor. If you double 64, it's too big, so that one's no good. 49 is not a factor either. We could try 36. Well, 36 times 3, 30 times 3 being 90, and 6 times 3 is 18, so that adds up to 108. So we could write this as the product of 36 times 3, okay? Now, if we look at what we did in the example above, one property of radicals is that when you have a multiplication statement, you can split it up into the square root of 36 times the square root of 3. And so our radical in simplest form is 6 square root 3. And we know this because if we go back to our conditions, well, there's no denominator, check. Okay, no denominator, check. There's no fractions. And then we just have to look at, are there any perfect squares that are factors of 3? Well, 3 is prime, so this would be our simplest form, okay? So all of these statements are equivalent, and we just wrote it in what's called simplest form there, okay? Let's make this a little trickier. Let's get a little trickier here. Let's say, for this example now, let's say we want to take the square root of 9x cubed. Okay, you're probably saying, oh, okay, well, Mr. Jones, let's split this into, let's find some perfect squares. Well, 9 is a perfect square, so we could write this as 9 times x cubed, and I say great. And then from there, we can split this up into the square root of 9 times the square root of x cubed. Okay, well, the square root of 9 is just 3. And so you say, all right, that's taken care of, check. And our question is, are there any perfect squares that could go into x cubed? And you might think, well, we're talking about variables here. How is this different? What would happen would you guys agree with me if I told you that x squared times x is the same thing as x cubed? And you say, oh yeah, Mr. Jones, that makes sense. So we can write this as the square root of x squared. Since this is a multiplication statement, we can split it up as the square root of x squared times the square root of x. Okay, well, our 3 comes along for the ride. The square root of x squared right here, well, that's just x. And then we're left with the square root of x on the end, because there's nothing we can do to simplify the square root of x. We'd be like, hey, what's the square root of 2? Well, the square root of 2 is just, there's no way to simplify it because there's no perfect squares that go into just x. So this would be our simplest form right here. Okay. So that's all good. Let's look at one more example. So if you notice, so far, everything we've talked about has been multiplication. If you look at our examples, there was multiplication going on here. It was multiplication going on here, and we were able to write it as a multiplication. We're multiplying two radicals here. I bet you can guess what's going to happen if we do a division problem. So let's say, for example, we have the square root of 15/64. Honestly, I don't know what that is. I would guess it's somewhere a little smaller than a half, but we'll find out what it is. If you plugged in a calculator, maybe it's 0.438 or something. But if you have a division statement under a radical like we do here, you can split it up into the square root of 15 divided by the square root of 64. Okay, well, the square root of 64, what number times itself is 64? And that's 8. So we have 8 as our denominator. And now we have to figure out, all right, are there any perfect squares? So let's go back to our list of perfect squares up here in red. Any perfect squares that go into 15? Well, 4 doesn't, 9 doesn't, 16 doesn't. So we're just going to leave this as the square root of 15. There's nothing we can do. There are no perfect squares that go into 15, so that would be our simplest form. Okay. Let's try one last one. Okay. New example here. Our last example, the square root of 81 over x squared. Okay. If you're doing this on your own, go ahead and pause the video a minute, see what you can, try it on your own, see what you can do, and then once you're ready, go ahead and play this and you can check your work. All right, so we can split this up. Since it's a division statement, we can split up as the square root of 81 divided by the square root of x squared. Well, the square root of 81, what number times itself is 81? Well, that's 9. And the square root of x squared, or what number times itself is x squared? Well, that's just x. Okay? So this one, in our simplest form, we actually ended without a radical in it. And that's okay. If that happens, great. That's even easier for us. Okay? So this is a little bit of work in simplifying some radical expressions. So hopefully you get a chance to try some of the homework. And if you have questions, feel free to email me and get in touch with me.